Okay, so we're going to pick up with the lesson we started on Friday. So on Friday, we learned about what a precipitation reaction is and what a precipitate is. And we also learned how to predict which product would form a precipitate if one were to form. So we're going to carry on and get into something called net ionic equations. Now, this is a topic that carries into grade 12 chemistry. It's one that you do a fair bit of in grade 12. So it's a good introduction into the topic. And this is a very detail-oriented process. So you have to kind of pay attention to all the little details here. So I'm going to walk you through the steps and we're going to do some examples together. And we're basically breaking down our usual balanced chemical equation into a series of steps. And one's called an ionic equation, and then one is called a net ionic equation. So let's look at what those topics are and what they mean. So ionic equations break every compound in a reaction down into ions, okay, except for the precipitate. Or other things that don't break down into ions are other solids, liquids, and gases. So you may be thinking to yourself, well, if solids, liquids, and gases, if none of those break into ions, what does break into ions? So only aqueous substances. So only things that are in solution. Only aqueous substances. Okay, everything else stays intact and our aqueous ones break down, and that's because an aqueous solution, if it has a dissolved ionic compound in it, that ionic compound separates out into its individual ions. We call that process dissociation. So the ionic equation actually shows the dissociation. So some of the ions are both, once you break them down, you'll see them as both reactants and products. You'll see them on both the left-hand side and the right-hand side. So because they don't change in the reaction, so you see them identically on the left side and the right side, both as reactants and products, we call those unchanged ions spectator ions. So they're like spectators. They're just watching the reaction happen. They're there before and after, and they don't actually join up with anything new or because they stay dissolved in the solution. So those spectator ions can be canceled out of the ionic equation to make what we call the net ionic equation. So net is kind of like at the end, like what's the simplest version of that reaction. Okay, so this all makes a lot more sense in a minute here when we walk through an example. So the net ionic equation is what we want to write out eventually for the reaction between copper 2 nitrate and sodium hydroxide. So our first step is we have to predict the products of this double displacement reaction. We have to decide, so basically we're going to do in step 1 what we were doing on Friday in our last lesson. We're going to write out the reaction, figure out the products, figure out if a precipitate forms, which product is going to be the precipitate, and then we're going to balance the reaction. Okay, so let's do that. Copper 2 nitrate is our first reactant. So copper, nitrate is NO3, and because copper has a +2 charge and nitrate's a -1, I'll do that. Okay, these are always, so even if it doesn't say a solution of for both the copper 2 nitrate and sodium hydroxide, When you're doing these reactions, your reactants are always aqueous solutions. So you can just add that in right away so you don't forget about it. Sodium hydroxide is NaOH +1 -1. Again, that's aqueous. Now we want to write our products. So it's a double displacement. So the copper is going to join up with the hydroxide, right, our outside ions. So it's copper 2 hydroxide. So we'll do this. I'm not going to yet label this because I don't know what state that's in yet. I have to check my solubility rules. And my other product is going to be sodium and nitrate to get together. So Na is a +1, NO3 is a -1, so those guys stay like that. So now, there's so many little itty bitty steps here, we don't want to forget anything. Everything has to be labeled with its state. Okay, so your reactants are always aqueous, but you need to figure out your products. So to do that, we go to our solubility rules chart. So one of our products was copper 2 hydroxide. So I'm going to skip down to hydroxide. I'm going to look at the middle column here. So copper is not an alkali ion and it's not listed here. So it would be in the all others category, which means it has low solubility. So that's telling me that copper 2 hydroxide is going to form a precipitate. So I'm going to write S there. For sodium nitrate, I want to find nitrate. And if you remember, this one will start to stick with you after a while because nitrate's a very common ion. Everything with nitrate is soluble. So anytime you come across a compound that has the nitrate ion, it's going to be aqueous. Okay, now before I can move on, I still need to balance this. So let's see. I've got 2 nitrates, so I need to put a 2 there. And then to balance out sodium and hydroxide, I could put a 2 there. Okay, so step 2 is write the ionic equation by breaking up aqueous species. So species just means like a compound. So if it's in the aqueous state, we break it up into its ions because this is an ionic compound, this is an ionic compound, and this is an ionic compound. So being aqueous means that these solids have been dissolved in water. So when you dissolve this one, and this one, they're going to separate out into their separate ions. So the copper ion and the nitrate ion, the sodium ion and the hydroxide ion. This one though, because it's insoluble, it won't dissolve in water. It won't separate, right? Because it's not soluble. So we're going to leave the precipitate intact. Okay, so we need to do a number of things here. We're going to break them up into their ions. We're going to show the charges of each ion, and we're going to use coefficients to keep them balanced. Liquids, gases, and solids are not split up. Okay, so again, lots of little details here to remember. So I'm going to separate this one out. So copper, we know it's the copper 2 plus ion. So I have to show the charge. And you always want to show your charges on the ions as the number, then the charge, okay? I also need to include the AQ symbol. So every time I break up an aqueous substance, I need to label each ion as aqueous because this is going to be dissolved, right, suspended in the solution. Now, I'm going to say plus. Now, the other ion is nitrate, but because there's 2 nitrates, right? There's 2 nitrate ions for every 1 copper ion. I need to actually state that. So I put it out front as a coefficient when I'm breaking up the ions, and I say 2 NO3, and each nitrate has a negative charge, and that's also aqueous. Okay, and I'm going to continue to do that all the way through. So for sodium, now there's a 2 in front of this whole entire compound here. So that 2 has to also be carried through down here. So I'm going to say I also have 2 sodium ions, each with a +1 charge. And that would mean I also have 2 hydroxide ions, each with a -1 charge. Okay, so I've continued to keep the number of ions the same as my balanced equation. 1 copper, 2 nitrates, 2 sodiums, 2 hydroxides because of this 2. Okay, so my reactants are all good. So now I go over to products. Well, this precipitate is insoluble, so we can't break it up. We're going to just leave it exactly as it is, and we have to still include the S. And then we're going to finally break apart the sodium nitrate. So again, there's a 2 in front, so that would mean I have 2 sodium ions. And I'm just going to carry down here. I also have 2 nitrate ions. Okay, so just notice the detail here. In order to have this step entirely correct, you have to make sure charges are included on each ion. You've got your symbols every time for every species, you might want to call it. Okay, so notice everyone's labeled with their state, and that you've continued to balance as we go. So that you've got, if there's a subscript, that subscript becomes the coefficient in front of that ion. If there's a coefficient, that coefficient carries through to both ions. Okay, so often when students do this step, they forget some details. So you just have to kind of keep a checklist going. What do I need to include here? Do I have it all? So you just have to be very careful. It's not difficult. There's just lots of steps. Okay, now if we look at step 3, this is our last step, we're going to cancel out all spectator ions. So the spectator ions are the ones that show up on both sides identically, meaning they're there at the beginning of the reaction, suspended in the solution, and they're also still there at the end of the reaction, suspended in solution. So it's like they're just hanging out watching, like as a spectator. So those guys, we're just going to eliminate and simplify this to its most basic or simplest form of what's happening. Okay, so if we look here, we can see 2 nitrate. There's also 2 nitrate ions on that side. So I'm going to say, okay, because those are just suspended in the solution at the beginning and suspended in the solution at the end, like nothing changed, I'm not going to write them out in my net ionic equation because they're just sort of present. They're not actually doing anything. The other one is the sodium. There's 2 sodium ions here and 2 sodium ions here. So those guys don't need to be included in this last step. We just want the bare bones at the end. Okay, so at the end, the net ionic is just writing out what's left. Okay, so we've got our copper ion and our 2 hydroxide ions, and they will form the copper 2 hydroxide precipitate. So that is all you write for the net ionic equation because that's all that's changed, right? All these ions, I'll just kind of draw it out here. All these ions would have been in solution to start with. You would have had your copper ion, you would have had 2 nitrate ions, you would have had 2 sodium ions, and 2 hydroxide ions. All these would have been dissociated in the solution once you added the 2 solutions together. After the reaction, okay, what you'd have is you'd still have the sodium ions suspended and the nitrate ions suspended, but you'd have your precipitate at the bottom eventually once it's settled. That would be the copper joining up with the hydroxide. So because that is really all that's actually changed, these ions stayed doing what they were doing. We're just showing what changed. That's the net ionic equation. The other stuff, they just were there, they were present, but they were just kind of hanging out watching, spectators. So the net ionic is showing what species actually changed during this reaction. Alrighty, let's try some more examples and hopefully you'll get the hang of this. Okay, so for practice, balance each equation first. Now, what you'll be told when you're writing out net ionic equations is you always do the 3 steps. Step 1 is known as the molecular equation, and in these practice examples, the molecular equation is given to you. Step 2 is called the ionic, and step 3 is called the net ionic. So sometimes they'll say, a question will say, write out the molecular equation, the ionic equation, and the net ionic equation. And sometimes for the molecular, like in the previous example, it'll just tell you the 2 reactants and it won't give you the formulas, it'll just give you their names, their chemical names. Okay, so in this case, the molecular formula is written for you. You're not predicting the products, but you need to finish it. There's no states included and it's not balanced. So you're going to finish off the molecular first, then you'll go on to the ionic, then finally the net ionic. Okay, so let's fill in our, I'm probably just gonna need a thinner line here so that I can sneak these in. So these are aqueous, always the reactants are aqueous. The products, I don't know. One's aqueous and one could be, now you don't necessarily always get a precipitate. You may not. It's possible to not get a precipitate. They could be both aqueous, so you always want to check. So let's look. We've got lead to iodide. So here's iodide. And if I look, well, there's lead 2, low solubility. Okay, so this is a precipitate, solid. And, well, if you remember, nitrate is always soluble with everything, but let's just prove that. Here's nitrate, essentially all soluble. So potassium nitrate would be aqueous. Now, is this balanced? Well, no, it's not. There's 2 iodines here, so I'm going to make 2 there. There's also 2 nitrates, and now I've made 2 potassium, so I'm going to put a 2 there. Okay. So now my molecular equation's done. I've got all my states written in and it's balanced. So for the ionic, I'm going to write out all the aqueous species are going to break up into their separate ions, and I'm going to make sure all charges are included, all states are included, and it's balanced. Okay, I'll just do that for this part. So let's just do one at a time. PB, there's no coefficient or anything, so I'm just going to put the charge, and that's aqueous. Now there's 2 nitrates, so 2 NO3 negative, aqueous. I'm going to break up potassium iodide. There's 2 because of the balance, so 2 potassiums plus 2 iodides. Then that side's good to go, and I'm going to do the next side. My precipitate in the solid state stays together, right? Anything that's not aqueous stays intact because it won't break up, it won't dissociate. And I've got 2 potassium ions and 2 nitrate ions. Okay, so in order to get to my very final step, I need to cross out the spectator ions. So what appears identically on both sides? Well, nitrate and potassium. They were just dissociated and suspended in solution before the reaction and after. So what actually changed was these guys who were once dissolved or dissociated joined together to make an insoluble compound. That insoluble compound becomes your precipitate, and because it's insoluble, it's no longer separated into ions. It's one compound, and it forms sort of that lump at the bottom. So let's write out what's left over. We've got lead, we've got iodine, or iodide, I should say, and finally lead 2 iodide precipitate. Okay, so let's do a few more. So here's our, I'll just go molecular, ionic, net ionic. So the molecular is written out for us with a few things missing. We need the states. So aqueous and aqueous for our reactants. Let's check our products. So barium hydroxide is 1. Here's hydroxide. Barium is listed here, and that says soluble. The other was sodium chloride. Here's chloride. Sodium's not in this list, so it's part of all others. So it's also soluble. So here's a situation where you don't actually get a precipitate. Both of these products are soluble, meaning they're both going to stay separated or dissociated in their individual ions. So this is going to look a little different than the previous, because every single compound is going to be broken up into its individual ions. So let's do that. Barium, and we've got 2 chloride ions. Oh, sorry, I didn't balance this yet. I better do that. We need 2 hydroxides. Okay, and then we need a 2 here to balance out the sodium and the chlorine. Okay, so that luckily didn't affect this. This is still all good, but this would look like that. 2 sodium, 2 hydroxide. And for these charges, you can always, if you don't know them off the top of your head, or you can figure them out from the compound, right? But you can also just look at your periodic table and your list of polyatomic ions to get the charges. So that's the other, I'm just kind of plopping them in really quickly, but I should also state that you would be looking to your periodic table to get these charges. Okay, so this whole other side is going to break up also because they're both aqueous. All right, now what is interesting here is when this happens, when there's no precipitate, these actually are all spectator ions because they're all just going to stay suspended in solution on both the before the reaction and after the reaction. So you're going to see, well, barium appears on both sides, 2 chloride ions appear on both sides, 2 sodium ions appear on both sides, and 2 hydroxide ions appear on both sides. So you essentially cancel out everything. So for the net ionic, what you would write is no reaction. Okay, so you may come across one like that from time to time. Okay, here's another type of scenario you might encounter. So here's your molecular equation. Luckily, this one, the states are there for us, so that saves us a bit of work. So we've got solid zinc mixed with hydrochloric acid, or HCl, which is aqueous, and this is a single displacement. So the hydrogen and the zinc switch places. So we get zinc chloride, which happens to be aqueous. So if we checked we don't need to because it's done for us, but if you look, chloride, zinc is not in this list. So therefore that's a soluble compound. And because hydrogen is part of Hofbrinkel, when they do the switch, zinc and hydrogen switch places, hydrogen ends up by itself. Whenever hydrogen's by itself, it is H2, and you just have to kind of remember that hydrogen all alone is always in the gas state, right? It's hydrogen gas at room temperature. So this one again is going to be a little different. So let's balance it. We need 2 chlorines, and that's it. Everything else is good. So for the ionic, well, anything that's not aqueous stays intact. So the zinc stays as is because it's solid. I'm going to break up the HCl because it's aqueous. I'm going to break up the zinc chloride because it's aqueous. Again, you always can check your periodic table for these charges. And hydrogen's a gas, so hydrogen doesn't get broken up. So do we have some spectator ions here? Remember, they have to be identical on both sides. Okay, so they have to look exactly the same. So zinc solid is not the same as the zinc ion with the positive 2 charge. So those do not cancel. I've got hydrogen ion, 2 of them. Well, that's not the same as this diatomic hydrogen molecule. Those are not identical, so I can't cancel those. The only one that's absolutely identical on both sides is the chloride, the 2 chloride ions. So when I write out my net ionic, I'm going to write out everything that's left. There's only one spectator here. All right. Okay, moving on. Here we have the beginning of our molecular equation, but we don't have the products. So let's finish off the products. So this is a compound plus another compound, so they're going to switch partners. So I'm going to take my outside ions, silver and chlorine, +1, -1. So these guys would stay put the way they are. I'll check out whether this is aqueous or not after. And the inside ions are going to get together. So potassium goes first because it's the positive one with nitrate. And now I'm going to go to my solubility rules and see how that works out. So if I look at chloride and I go across, silver is listed here, and that's under low solubility. Okay, my other compound was, what was my other one? Potassium nitrate. So remember, nitrate is soluble with everything. So when I go to do that one, Here's my precipitate. This one's aqueous. Now I just have to balance if necessary, and it looks like everything is already balanced. So for my ionic, I'm going to break apart all my aqueous substances into their individual ions. Silver has a +1 charge. Nitrate, -1. Potassium, +1. Chloride, -1. On the other side, silver chloride is the precipitate. I don't break it apart. And I'm going to break up potassium and nitrate. Okay, now let's cross out spectators. Well, I've got potassium ion on both sides, and I've got the nitrate ion on both sides. So my net ionic is just what's left. Silver plus chloride ion produces silver chloride. Okay, so hopefully that gave you enough different examples that you can try this on your own now. So the worksheet that I assigned on Friday, I just had you do question 1, deciding whether the substance is soluble or insoluble. So that was just a matter of checking your solubility rules. You can go on to finish the rest of the sheet now, and it would involve doing these 3 equations for each question.